This is the review session for EGME 410 for the fall 2021 semester for the first and only midterm for this class. Okay, and so I want to start this video off by apologizing because I kind of forgot this week to put out a poll for you guys to vote on topics, but I think it's okay for this one because the amount of content that we're covering for this midterm is not as much as my previous classes, and so even if I put out a poll, you choose 2 out of 3 of these, and then there's only 3 topics. So I thought I'd just kind of just do a review of all of them. Okay, all right, and so let's go ahead and get started. All right, and so we have basically 3 sets of lecture notes that you're going to be responsible for on this midterm. And so what I thought I'd do is I'd kind of go over each one for maybe about 20 minutes each, kind of go over kind of the most what I think most essential topics or most essential concepts that you need to know from these, and maybe do a couple of examples along the way. Okay, all right, so let's start with the direct stiffness method, which is kind of our first foray into kind of finite element theory. Okay. All right. And so you can think of this set of lecture notes as kind of like the introduction to basically what how finite element computations are performed. Okay. Okay. All right, and so one of the big ideas that I want you to take away from this set of lecture notes is just kind of the overall process of how you do a finite element computation by hand. Okay, and I say by hand just because that's what I'm expecting you to do from this unit. But really, this is kind of what's been done. This is kind of what's being done underneath the hood in ANSYS as well. You just don't explicitly see it because they put a very nice GUI on top of it. Okay, but basically, the whole finite element process kind of goes something like this. Okay. Right, and so the first step in the finite element process is to first of all just kind of take stock of your problem. So to look at the geometry and see what boundary conditions are being applied. Okay. Okay. And so in terms of the computations for this class, those will be given to you. Okay. And so when the geometry is given to you, it's already going to be discretized into different elements. Okay. And so given that information about the elements and knowing the properties of all those elements, the next step is to compute all the element stiffness matrices for each of the elements. Okay, and so once those those element stiffness matrices are computed, based on the material properties, the geometric properties of the elements. Okay? And so you're going to see some quantities in there, like the spring constant, like the cross-sectional area, the length, the Young's modulus, moment of inertia, right? So all of those things are properties of the structure itself, of the element itself. Okay, and so that's kind of an important thing to remember, and we'll come back to the idea, in a little bit as well. Okay. All right, so number three is once we have the element stiffness matrices for all the elements, the next step is to assemble. Okay. Okay. And so what I mean by assembly is that, we take all the element stiffness matrices and put it all into one big, linear system. We call this the global linear system. Okay. And so, this global linear system is ultimately what we're going to be solving in the end. Okay. Right. But in this current state, right after you assemble the element stiffness matrices, it's actually not solvable yet, because the global linear system is a symmetric matrix, right? And if you try to invert a symmetric matrix, you're going to get nothing, because the determinant of a symmetric matrix is always 0. Okay? And so in order to make the system solvable, we have to apply our modes and constraints, or in other words, our boundary conditions. Okay. And so, those will be things like, where do we apply our fixed supports, which nodal degrees of freedom are going to be fixed, and, which nodes are we going to apply our loads. Okay. Okay. And step 5, we can solve. Okay. And so once we applied our boundary conditions, then our global linear system will, will be able to be solved, and we just, punch it into MATLAB and let it do its thing. Okay. And so, this whole process here, this whole finite element process, you're going to be following this process, for all the problems that are being solved. Okay. The only big difference between between all the different units that we're covering is really step 2. Okay. And so, how you compute the element stiffness matrix depends on what kind of element that you're working with. Okay. Okay. And really, actually, the big difference in this whole process between, what you're doing on paper and what ANSYS is doing in its programming is really just is step 2. Okay. And so in step 2, the way that ANSYS computes its element stiffness matrices is really different. Okay. And actually, the big simplification that we're making, for these calculations is really in step 2. Okay. And so when people say the direct stiffness method, what they really mean is that they're getting a direct formulation of the element stiffness matrices, kind of based on the physics of the problem. Okay. And so, other forms of finite elements, other methods basically use different methods for deriving this element stiffness matrix. It's just, different methods yield different element stiffness matrices. Okay. But then the process of, looking at your geometry, assembling the global linear system, applying boundary conditions, there's actually, a lot of similarities. And I actually would believe that ANSYS does that in very similar ways. All right, and so with that, let me take a look at this global linear system, right? So that we can talk about, what goes into each of those terms. Because I think that's really important to understand conceptually about what's going on in this whole scenario. Okay, and so when we have a global linear system, or even an element system, we have something that looks like the following. Okay, and so we have a vector by itself. Okay, and so we call this the right-hand side forcing vector. Okay, then we have a stiffness matrix. Okay, and so that could be an element stiffness matrix, or it could be the global stiffness matrix. And then we also have D, which is our solution vector or our response vector. Okay. right? And so I'm bringing this up because I want you to conceptually understand, these three components of a finite element linear system and what kinds of things go into each of these components, okay? And so let's start from the left and kind of go to the right, okay? So let's start with the right-hand side forcing vector, okay? And so, the reason this is called the forcing vector is that what goes into this vector here is basically all of the external effects that are acting on our structure. Okay. And primarily, the only external effect that we're really considering are the boundary conditions. Okay. And so things like loads, things like constraints, right? All of those effects go into the forcing vector. Okay. For the stiffness matrix, let's just kind of take a minute and list out all the quantities that go into the stiffness matrix, right? And so this is universal, right? And so we basically looked at springs, we've looked at truss elements, and we looked at beams, right? And so we have constants like spring constants. We have Young's moduli. We have area. Okay, length. And in the case of beams, which is unique, we have the moment of inertia of the cross section. Okay. Right, and so there's a lot that can go into an element stiffness matrix, and if you look at different kinds of structures, other things can go in here as well. Okay, but there's kind of a unifying theme behind all of these quantities, and I hope that you see it. And so the whole unifying theme between these are all I would say inherent properties of the structure itself, independent of any kind of external effects. Okay. Right. And so things like geometry, things like the material properties, right? All of these get factored into the stiffness matrix, okay? And so no matter what kind of loading that you have, right? Whether you apply fixed constraints here or there, or you apply loads here or there, like that doesn't change who what the structure is, right? And so basically any property of the structure that doesn't depend on anything external will go into the stiffness matrix, okay? All right, and then finally, we have the response vector, okay? And so the response vector, for our case, since we just focus on structural mechanics, the response vector contains things like the deformations, okay? Okay, and the reason I call it the response vector is that it's kind of a result of, we have this structure, we have the structure with all its own properties, that make the structure who it is, right? We have its geometry, its material properties, okay? And then onto that structure, we're going to be applying external effects from the loading, right? And so the response vector is basically how the structure itself responds to the external loadings, okay? Okay. And so that's those are the three components, okay? And I wanted to make this distinction really clear because I think it's really important to understand, just from a conceptual point of view, all these different aspects of finite elements, okay? Because these are all things that we've looked at in ANSYS as well, right? And so the stiffness matrix, that would be comprised of, properties based on the geometry itself. Okay, so the CAD model on its own, will contribute something to the stiffness matrix along with whatever material properties that you choose. All of the boundary conditions that you apply, that gets factored into the forcing vector. And then after we hit solve on ANSYS, all the deformations and all the stresses, that comes as a result of the response vector. Okay, and so I always find it useful that when I'm doing finite elements, think of finite elements as these three quantities together. Okay, and to make the distinction between them. Okay. Because it's helpful, because like when you're running a finite elements and you're changing something like geometry, that it's gonna make a difference in the stiffness matrix. Okay. All right. And so that's kind of the the three aspects of a finite element problem in general. Okay. And so I didn't want to do any problems for this one yet, because the problems are kind of 1D and kind of relatively simple, and so we'll save that for the next one. But let's go ahead and move on to our next topic, which is truss equations. Okay, and this is kind of where a big bulk of the calculations are taking place. All right. And so truss equations, I would say this is kind of the first unit where we're really doing some pretty heavy finite element calculations, right? And it's all centered around, what we call to be truss elements. Okay, so I think conceptually, the first thing you should understand from this unit, or from this set of lecture notes, is what a truss element is and how we assume that it deforms. Okay? And so the big thing that we assume with truss elements is that we assume that their deformations are limited to the axial direction. Okay. And so what that means is that, we assume that the only ways for them to deform are either in compression or extension. Okay. And so visually, we have an element that looks like this. Okay. We're going to assume that we have deformation, or let's say we have a forcing T in both directions. Okay. Right, and so what we have here is that if the forcing is limited to that direction, then our deformations can be limited in that direction as well. Okay, and so we're basically under the assumption that any kind of transverse deformation is not going to be active. Okay, and so truss elements are very similar to springs, right? So for a spring, you really only imagine yourself kind of compressing the spring or pulling the spring apart, right? And so trusses and springs are kind of two peas in a pod. It's just kind of the way that their element stiffness matrix is computed is slightly different. Okay. All right, and so the element stiffness matrix for a truss is based on its properties. Okay. And so the properties of a truss element that are relevant to its stiffness are its cross-sectional area, its Young's modulus, and its length. Okay. All right, and so its expression is given by the following. And so, for a 1D truss, right? And so the element stiffness matrix is going to be AE over L times 1 minus 1 minus 1 and 1. Okay. Right. Where this quantity out in front right here, AE over L, sometimes people call this kind of like the effective spring constant of a truss element. Okay. All right, and so that's the that's the quantity there. Okay. All right, and so that's the conceptually what a truss element is. And so before we jump into an example problem, let's talk about some of the adjustments that we have to make in 2D. Okay. Okay. All right, and so in 2D, the big difference that we have here is that we consider deformations in directions that are more than just 1D. Okay. Okay, and so what that basically means is that our deformations are now going to have two components. Okay. And so this is actually a little bit more realistic to to how deformations are actually computed in finite element software as well. Okay, and so when ANSYS computes its deformation, excuse me, it's actually computing a deformation vector, right? And so the vector, just like any vector, has components, right? And so I think the 2D truss equations that we do do a good job of illustrating this fact. Okay. All right. So visually, it looks something like this. Okay. And so we can break up the deformations in this at each of these nodes. Into an X component and a Y component. Okay. And so basically at each node, we're going to be solving for two quantities. Okay. And so, even though we're solving for two quantities at each node, we still are under the assumption that the deformations are purely axial, right? And so, if we draw this in, in terms of the local coordinates, it still looks like this, okay? But the reason we break it up into components like that is so that we can work under what's called the stationary and consistent coordinate system, okay? Right? Because when we're doing problems like these, we're going to have elements that are oriented in all different directions, right? And so in order to basically compute their values or to basically assemble them together into the same system, we have to do that all under a consistent coordinate system of measurement. Okay, and so that's kind of the purpose of the stationary coordinate system. Okay? And so it does seem like a lot of work to work in conditions like this, because we're computing two things instead of one at each node, but it's kind of a necessary evil, in order for us, or I shouldn't say evil, it's not an evil, it's a necessary step for us in order to compute problems like this. Okay, right. And so what does this mean for our element stiffness matrix? Okay, and so basically what we're doing is we're characterizing the direction of the truss element in terms of the angle that it makes with the horizontal. Okay, and so with that in mind, then our element stiffness matrix is the following. And I'm going to use shorthand notation here. And so I'm going to use the letter C to denote cosine theta, and the letter S to denote sine theta. Okay. And so the element stiffness matrix is equal to AE over L. Okay. And so that guy stays the same. Okay. And then we have a 4x4 element stiffness matrix. Okay. So we have cosine squared, cosine sine, minus cosine squared, minus cosine sine. Okay. Sine squared, minus cosine sine, minus sine squared, cosine squared, cosine sine, sine squared. Okay. Okay. And of course, I only drew half of the element stiffness matrix because the other half is symmetric. Okay. All right. One note, and this is a really important note. And so, this is, really important for everyone to know that when you compute this angle theta, make sure you're computing that appropriately. Okay. Okay. And so the angle theta that you plug into here is always with respect to the positive x-axis. Okay. And that's considering the fact that you draw a vector arrow from the lower numbered node to the higher numbered node. Okay. Because I think classically a lot of us are trained to only consider angles between 0 and 90, right? Because that's usually the smallest angle that you can use to describe something. But when you're doing these finite element problems, you want to make sure that you define the angle correctly. Okay. So let me just do a couple really quick examples to kind of illustrate this. Okay. Right. And so let's say that we have an element that's angled like this. Okay. And so let's say that we have element one, node 1 here and node 2 here. Okay. And in the figure, you might see, the figure kind of define the angle as theta right here. Okay. Right. And so, when you're given an angle theta like this in the geometry, it's really tempting to just take that angle and plug it right into the equations. Okay. Okay. What I'm telling you is to kind of resist that notion. And so what you should do is that you should draw an arrow basically from node 1 to node 2 like this, okay? And then also draw the positive x-axis emanating from the lower numbered node, okay? And so in this case, the lower numbered node is node 1, okay? And so, draw a point at node 1 and then just draw a line horizontally to the right from there, okay? And so this is the positive x-axis, okay? And then the angle that you should plug in is actually going to be what it takes to rotate from the positive x-axis over to where your vector is right now, okay? And so in order to get to this orientation, we have to rotate all of this amount, okay? And so the true angle, okay, the one that we actually plug into our element stiffness matrix is actually, we can see here that we rotate 180 degrees, okay? And so whenever we make a half rotation like that, it's gonna be 180 degrees, okay? Plus the angle theta that's shown in the figure. Right, and so you want to make sure that you plug this angle into the expression on the previous page, because it's going to change some signs of the cosine and sine terms. Okay. Because in this particular case, if we, and I think of these always in terms of quadrants, right? And so if we draw kind of a coordinate axis right here, this is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4, right? Or maybe it's numbered differently, I don't remember now. But basically, if you haven't seen this trick before, you can predict the signs of or predict whether positive or negative for cosine sine based on what quadrant you're in, right? And so in quadrant 1, both cosine and sine are positive, right? Because we're in the positive half of both of those terms, okay? Remember, cosine is usually most associated with the x component, and sine is usually most associated with the y component, okay? In quadrant 2, we're still above the x-axis, but we're to the left of the y-axis, okay? And so in quadrant 2, cosine will be negative, while sine will be positive, okay? In quadrant 3, both cosine and sine will be negative, okay? In quadrant 4, cosine will be positive, while sine will be negative, okay? And so it's important to get these signs correct, because if you don't get the signs correct, you're going to get completely wrong answers for this element stiffness matrix. Okay, and so I think that's all. I mean, there's other stuff in here too, but in terms of what I'm expecting you to do for the exam, let's go ahead and jump into an example problem. Okay. Okay. And so this example problem will be coming from the homework. Okay. And it's going to be the one that is unsolvable. And so it's going to be, what is that? I think that's problem 3B. Okay. And so I'm going to do this in the style of what I'm going to expect you to do on the on the exam. Okay. And so basically I'm going to be constructing the element stiffness matrices, and I'm going to be assembling it and applying boundary conditions, and then that'll be okay. All right. And so in this problem we have 3 truss elements and a spring. Okay. And so we have one element that looks like this, another element that looks like this. Okay. So these are truss elements. We have a spring element like so. And we have another truss element like that. And so we kind of have this like triangle sail type thing. Okay. All right, we have a pin support here. Pin support here. This is node 1. This is node 2. This is node 3. This is node 4. Okay. This is element A. This is element B. Element C. Element D. Okay. All right. And we also have the material properties. And so I think what I said was that the Young's moduli for all the elements is the same. Okay, so we're going to assume that the Young's moduli are 12 megapascal. Right. And so the lengths of the elements, which are relevant for the trusses only, for A and B, we have the same length. And so that's going to be 2.4 meters. Okay. Meanwhile, element C will be 3.4 meters. Okay. We're going to assume the cross-sectional area for all the elements is the same at 0.1 meters square. Okay. Let's see. The spring constant for element D, because it's a spring, is 500,000 newtons per meter. So I'll say 500 kilonewtons per meter. Okay. And we have two loads here. Okay. And so we have a compressive load here, and so we'll call that PX. And then we have another compressive load from the top, we'll call PY. Okay. And their values are PX is equal to 500 newtons, while PY is equal to 1,000 newtons. Right. And this angle right here, I always forget to mention this. Okay, so this angle right here is 45 degrees. All right. And so, we're gonna progress through this problem, as if it were an exam problem. So we're going to construct the element stiffness matrices for each element. Then we're going to assemble it all into a global linear system. And then we're going to apply the boundary conditions. Okay. All right. So I will say, at this point that, this problem right here is more than I would expect you to be able to do on the exam. Because there's 4 elements here, okay? And so 4 elements is 4 element stiffness matrices, okay? And so I'm aware that, during the exam, you have a very limited amount of time. And so I don't want you to spend a lot of that time just kind of tediously writing stuff down. And so I'll tell you right now that, all the problems on the exam, or at least, for the 2D problems and for the beam problems, have 3 or less elements on them, okay? All right, but let's go ahead and do that for this one just so that we know what to do. All right, so part A is element stiffness matrices. Okay, and then we're going to go element by element. Okay, so element A, right? So element A is kind of pointing vertically upwards, and if we draw an arrow going from node 1 to node 2, we can see that the angle that it makes here is 90 degrees. Okay. Okay. And so if you have an element that's either 90 degrees or 180 degrees or some multiple of pi over 2, you're in good shape because the element stiffness matrix, a lot of it's going to cancel out. Okay, because the thing with 90 degrees, that cosine of 90 degrees is going to be 0, and sine of 90 degrees is going to be 1. Okay. And so this simplifies your life a lot because if you go back to our expression for the element stiffness matrix for a 2D truss, basically any term here that has a cosine, we're just going to set it equal to 0. Okay, and so like we can say that this entire first row is going to be 0. These two guys are going to be 0. This one's going to be 0. And so the only ones that are not going to be 0 are the sine squared terms. Okay. And so if you spot patterns like that, it can save you a lot of time in writing these out. Okay. All right. Oh, first let's compute EA over L. Okay. And so for element A, if we compute the quantities EA divided by L, what we get is 5 times 10 to the 5th. Okay. All right. And the way that we got that was I took 12 megapascal, I multiplied by the area, which is 0.1 meters square, and I divide by the length, which is 2.4 meters. Okay. And so the element stiffness matrix here is going to be 5 times 10 to the 5th. Okay. And so I'm putting shorthand for that as 5E5. Okay. And then the element stiffness matrix. Okay. Remember that entire first row is zeros because those are all the cosine terms. Okay. And remember the other trick that I taught you too is that because it's symmetric, what you can do is you can kind of build up the element stiffness matrix row by column. Okay. And so when you write the first row like this, you can assume that that first row is also going to be the first column. Okay. And so because we have 0, 0, 0, 0 in the first row, then our first column is also going to be 0, 0, 0, 0. Okay. Just like that. Okay. All right, second row. And so second row, we have a sine squared on the diagonal. And so sine squared, we have 1 squared, which is 1. Then we have a cosine sine term. I believe it's a negative cosine sine. Yeah, negative cosine sine, but it doesn't matter anyway because it's just 0. Okay, negative 0 is still 0. And then we have a minus sine squared, which is just minus 1. Okay. And so just like we did for the first row, we're going to write this into the second column. And so we have 1. We're going to bring the 0 down here. And then we have minus 1 that we're going to put in the last row, just like that. Okay. Right. And so for the next row, we have 0, 0, right? Because that's a cosine squared and a cosine sine. And so we draw that into the last column right there. And so that's going to be 0. And then, in the bottom right term, we have a sine squared. Okay. So that's just going to be 1. Right? And since this element here acts on nodes 1 and 2, we have a u1x, u1y, u2x, u2y. Okay. Right. And so if you have a element like this, then you can rejoice because it'll be nice and simple. Okay. All right. So let's go on to element B. So element B, the orientation is exactly the same, and so the element stiffness matrix is actually going to be identical as well. The only difference is the nodes that it works on. Okay. Okay. And so KB is equal to, oops, sorry. Equal to 5 times 10 to the 5th. Okay. And then we're going to just write out the same element stiffness matrix. Okay. Let me just go and do that really quickly. Okay. But element B is going to be working on different degrees of freedom. And so element B is working on nodes 2 and 3. And so we have a u2x, u2y, u3x, u3y. Okily dokily. All right, and so now we come to element C. And element C is kind of the tricky one here. Okay. All right, so element C is oriented like this. Okay? And so we have node 3 right here. Okay, and we have node 4 right here. Okay? Now let's do the way that I kind of just mentioned to see what angle that we need to get to in order to get to here. Okay. All right, and so because this arrow is pointing kind of down to the right, we basically know that we have to rotate all this way in order to get to that point. Okay, and so the angle here is actually going to be that entire angle. Okay, but what is that angle? Okay. And so in the problem, I gave you kind of a vertical, an angle with respect to a vertical, and so we know this angle here is 45, right? And that's given in the problem. Okay. And so the total angle for this element here is going to be, this rotation right here, right? Let me use a different color actually. Okay. And so it's going to be that rotation plus 45 degrees. Okay. And so since in the purple right here, we have a 3/4 rotation, a 3/4 rotation is 270 degrees. Okay. And then in the blue, what we have is another 45. And so we're going to add 45 degrees to this. Okay. And so that's going to be 315. Okay. All right. And so with that in mind, and knowing that we ended up in quadrant 4 right here, we know that the cosine should be positive. Okay. So the cosine is going to be positive √2/2, and the sine is going to be negative minus √2/2. Okay. All right. And so let's go ahead and plug that in. We have another EA/L here. Okay. So the length for element C here is longer. And so that's going to modify our effective spring constant. Okay. All right. And so the element stiffness matrix for C is going to be 3.53 E5. Okay. And so if we plug in, a positive √2/2 and a minus √2/2 into the first row, what we get is 1/2 minus 1/2, minus 1/2, 1/2. Okay. And once again, I'm going to write this into the first column. So that's minus 1/2, minus 1/2, 1/2. Okay. Then we have 1/2 here, 1/2 here, minus 1/2 here. Okay. I'm going to write those values into the first column. So we have 1/2 and minus 1/2. Okay. Okay. We have a 1/2 here, minus 1/2 here, minus 1/2 here, and 1/2 here. Okay. All right. And so this is going to be working on nodes 3 and 4. Okay. And so this is going to be U3x, U3y, U4x, U4y. Okay, so that's element 3, or element C, I'm sorry. Okay. And now we have element D. And so element D is our spring. Okay. Right. So element D looks like this. Right. And so, our angle here is going to be 0, right? Because it basically aligns perfectly with the positive x-axis. Let me show you a shortcut for this. And you could have applied the shortcut to actually elements A and B as well. Okay. And so in cases where, your angle is going to be 0, 90, 180, or 270, what is that a lot of the elements in the element stiffness matrix, or a lot of the entries, are just going to be 0 anyway. Okay. And so if you actually boil it down, the only non-zero entries are these ones right here. Okay. And so if we were to actually write out the full element stiffness matrix for element D, it would look something like this, right? And so element D, the spring constant, by the way, was 500 kilonewtons per meter. And so that's going to be 5E5. Okay. And so the full element stiffness matrix would be 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. And since this acts on nodes 2 and 4, then we have those degrees of freedom right there. Okay. We can actually simplify this, and so it could save you a little bit of writing, but you have to be a little bit careful when doing this. Okay. And so because this is a perfectly horizontal element stiffness matrix, you can reduce this to actually a 2x2 system. Okay. And so what you can say is this is going to be 5E5, okay, and our usual 2x2 element stiffness matrix. Okay. But you have to be careful about what degrees of freedom that you put in here. Okay. And so if you notice, the only lines that are active are going to be U2x and U4x. And so this might save you a little bit of writing if you're a little bit savvy on how you compute those. But you have to be careful when you assemble this, because you're not going to do kind of one contiguous block anymore. You're going to do 4 entries that are kind of far from each other. Okay. And I'll show you how to do that on the next page. Okay. All right. And so let's go ahead and do the next part of this problem, which is assembly. Okay. And so under assembly, in this particular case, we have an 8x8 system because we have 4 nodes. Each node is 2 degrees of freedom, and that means we have 8 degrees of freedom overall. Okay. And so let me go ahead and write out all of the rows here. Okay, so we have U1x, U1y, U2x, U2y, U3x, U3y, U4x, U4y. Okay. Right, so barely fits here. And I'm going to draw the rows in there as well. Okay. All right, so let's go ahead and highlight the areas where things are going to be. Okay. All right, so let's do element A first. So element A is acting on nodes 1 and 2. So let's go ahead and highlight all of those rows and columns. Okay, and so element A is just like that. Okay, right, and so we take in all of the U1X, U1Ys, U2X, U2Ys. Okay. All right, so element B is taking care of nodes 2 and 3. Okay, so let's go ahead and highlight all of those. Okay. And so, we can see that we have a little bit of overlap right there. Okay. Next, we have element C. Okay, element C is going to be nodes 3 and 4. Okay. So we're just going right down the line. Right, just like that. Okay. And then finally, we have element D, right? And so this is where you kind of have to be careful. Okay. And so with D, what we said, this only acts on U2X and U4X, right? And so what that tells us is that, we're going to go to all the columns that have U2X, okay? And so U2X, we go to U2X, U2X, and so we see that, we have an entry right here, okay? Then we go to U2X, U4X, and so that's an entry right there, right? Because that's the U2X column, U2X row, U2X row, U4X column, okay? Then we go to the U4X row and the U2X column. And so we have that one right there, okay? And then finally we go to the U4X column, U4X row, which is that one right there, okay? All right, and so we insert only 4 entries into the stiffness matrix because our element stiffness matrix was only 2 by 2, okay? And so if you're going to use that shortcut, you have to be careful in this. And you have to be careful not to do, in this case, because our element was horizontal, that we don't do any entries in the Y degrees of freedom. Okay. All right. And so let's go ahead and add all our entries in here. Okay. All right. And so I'm just going to do the result of all of these. Okay. Okay. And so we have 5E5, 0 minus 5E5. Okay. 0, 0. 0 minus 5E5. Okay. So this would be 5E5. Okay. So this only has contributions from the spring. Okay. We have 0, 0. 10E5 here. Okay. 0, 0, 0 minus 5E5. Okay. This is minus 5E5 minus 5E5. Okay. 0, 0, 0 minus 5E5. Okay. Here's where things get fun. And so, we need to do a lot to add here. Okay. Let me do this just to kind of save on writing, because we are getting a little short on time. I do have an appointment later. Okay. So I'm going to use the variable x represent 1.76E5. And the way I got that was basically, we have this 3.53E5, and we're going to be multiplying by a bunch of 1/2s in there. Okay. All right. And so here we have x minus x minus x. We have x plus 5E5. Okay. We have minus x, x, x minus x. We have minus x, x, x minus x. x plus 5e5, okay, minus x, x, okay, and then everything else is zeros. Okay. All right, and so that's how we assemble. Okay. All right. And so this would be kind of like a part B of the problem I would ask you on the exam. Okay. Part C, and the last thing that I would ask you to do would be to modify this matrix for the boundary conditions. Okay. And so for this review, I'm going to do it just kind of in line here, and so I'm just going to erase and add ones. But for the exam, I actually want you to do this as a separate one, just so I can see first of all, what your assembly looks like, and I can see what it looks like after you apply the boundary conditions. Okay, so do as I say, not as I do in this case. Okay? But in this particular problem, we have fixed supports on node 1. Okay, or I guess it's a pin support. Okay, and a pin support on node 2. Okay, and so to change this, we're going to have a 1 right here, a 1 right here. Okay, and change everything else to zeros. We're going to have a 1 here, change everything else to zeros. Okay, we're going to have 1 there, and change everything else to zeros. Okay. And so again, make sure that you actually, write that in on your, or make sure you make a whole new matrix on the exam, but for here, I'm just writing it in just because it's, it's a little bit convenient. Okay. And in terms of the loads, we have 2 loads here. And so we have one load acting on U3Y, okay? And so on this row of the global stiffness matrix, or global linear system, we're going to put a load of minus py over there, okay? And then we also have a load acting on this node right here, which is the boundary condition for U4x, okay? And so we put those boundary conditions on the other side of the system, okay? All right, and so that's how you run through a problem kind of front to back. Okay? And so I know that took a little bit longer than I thought, but hopefully some of the first of all, just kind of seeing the whole process from front to back was useful, to kind of see how it's done, and hopefully some of the little tricks that I gave you along the way will help you save a little bit of time, because I know time is going to be an issue just because there's kind of a lot to write down and a lot of computation to do. Okay, and so any little bit of time that you can save on the exam, I think will be good. All right, and so with that said, I do want to move on to beams really quickly, and so I only have about 5 minutes, and so I think for the beams, I'll tell you right now, for the beams, I'm not gonna expect you to do any kind of distributed loading, okay? And so it's just going to be a beam with point loading. Okay, and so you won't have to worry about doing that on the exam, just because it just kind of takes way too long to do. Okay, and so instead we're going to focus on just what makes beams different than truss elements, and we're going to look at its element stiffness matrix as well. Okay, all right, and so let's do the first point first. Okay, and so beams are different. Beams are different than truss elements in that their deformations are basically everything that a truss does not do. Okay, and so a beam has 2 degrees of freedom per node. Okay, and so the first degree of freedom is a transverse displacement. Okay, and so a transverse displacement, remember, is a displacement that's perpendicular to the beam. Okay, and number 2 is we have a rotation. Okay, and really the rotation is what makes it unique, and I think that's kind of the connecting thread between what we're covering theoretically here, and what we did for activity 4, which is shell and beam elements. Okay. All right, and so visually, it looks something like this. And so for beam elements, usually I use some kind of rectangle to denote it. Okay. And so if we call this node 1, call this node 2. Okay. All right, so we have a transverse displacement. Okay, and so those are displacements that are perpendicular to the beam. Okay. Okay, and we also have the rotations. Okay. Right, and so it's important to kind of understand conceptually what these rotations are. And so what these rotations represent is they represent kind of the orientation of the beam at these locations. Okay. And so it's one thing to say, what the deformation is over there, what the displacement is, but it's another thing to say, what the angle or what the orientation of the beam is over there. Okay, because it's possible to have a displacement that goes up like this, but the beam might be kind of concave downwards over there too. Okay, and so it's the combination of these two things that makes the beam formulation a little bit unique. Okay, and if you recall from activity 4, this rotation is kind of what makes shell and beam elements unique from our solid type elements. Okay. And it's because of these rotations that that beam elements can compute stresses and strains a lot more accurately than solid elements when the geometry is really thin. Okay, and so unfortunately we can't really get into the theory about why that really is, but that's kind of the unique thing. And so when you have solid type elements, when you have like tetrahedrons and your hexahedrons, they're not computing these rotations. Okay, and so that's the big difference there. Okay. All right, and so the last thing we're going to look at is we're going to look at the element stiffness matrix for the beams. Okay. Okay. And the beam element stiffness matrix, I admit is a little bit tedious because it is a symmetric matrix, but the pattern is a little bit difficult to really get down because of because the deformations have units of lengths, but the rotations don't have any units. And so even within the element stiffness matrix, it's a little bit inconsistent. Okay. And so before we jump into that, we do have one additional property that's needed for beams, and that's the moment of inertia. It's the moment of inertia of the cross section, which we give the symbol I. Okay. Alrighty. And so the way that we compute this, or let me sorry. So I kind of got ahead of myself a bit. Okay. And so what this I represents is it's kind of a representation of how mass is distributed in the cross section of the beam. Okay. And so if you have like an I beam like this, okay, versus maybe a cylindrical beam, okay. And so mass is distributed differently in these two beams, in these two beam cross sections, and that basically affects how the transverse displacement and the rotation are. Okay. And the way, and different distributions of mass are basically encapsulated by that moment of inertia. Okay. All right, and so the element stiffness matrix for a beam, what we have is we have the product of the Young's modulus and the moment of inertia, okay, divided by the length of the beam cubed, okay, and it's going to be multiplied by the following. Okay, so we have 12, 6L minus 12, 6L. Okay, and I'm going to do this, in the same style that we did from from before. And so once we have the first row, you can go ahead and write that into the first column. Okay, so we have 6L minus 12, 6L, okay, 4L squared minus 6L, 2L squared. Okay. Oh, and let's go ahead and write that into the to the next column. Is we have minus 6L, 2L squared. Okay. Then we have 12 minus 6L minus 6L, and we have 4L squared. Okay. All right. So that's how, and so that's how you write out this element stiffness matrix. Okay. All right. And one more thing I recommend that you review from the notes is for situations where we have combined beam and truss or spring elements. Okay. And so there is an example of that in the notes. And so let me scroll. There's an example of a situation with two beam elements and a spring. And so actually on page 6, at the bottom of page 6 of the beam equation notes. And so I actually do recommend that you check that out, just so that you can see how those are combined. Okay. But with that said, I am out of time here. And so, it's been about an hour. And so, that's all the time we have to review. And so, hopefully this review video was helpful. Because and I know I tended to focus a lot more on the conceptual stuff here. But I think that's important to know because the homework was very long. I think it's very easy to kind of get lost in the calculations and then kind of and get into like a rhythm or of just what the process is. Okay. And so the whole reason, remember, the whole reason I'm having you go through this theoretical part of finite elements is to basically not get stuck or not get not think of finite elements as kind of like this black box where you just have to go through the motions. Okay. And so I don't want you to just go through the motions in this class. Right. So part of the reason you take a class in finite elements is that you have on the one hand, like you learn how to apply it in the software at a professional level, which I think you guys are all getting there really well. Okay. But also have a good understanding of what's going on underneath the surface from a methodology, from a theoretical standpoint. Okay. And so I don't want you guys to just go through the motions of doing these problems. So I want you to also really understand why you're going through these and what each step kind of represents. Okay. And so that's what I wanted to focus on mostly on this review. And so hopefully that was helpful for that. Okay. All right. And so, if you have any more questions on the exam, please don't hesitate to reach out. I'll be answering my emails as quickly as I can. With that, best of luck studying, and I will see you guys next week.